construction wise, DC generator and DC motor have the same construction, and how we use it depends upon what are the conditions, what are the inputs we are giving, and what are the outputs we are taking. So either way the construction is constant. So we have seen what are the different types of main components, principal components we need a field system, we need an armature core, we need an armature winding along with a commutator and brushes. These are the basic five principal components that are required for a DC machine. This we have seen, right? In this in this we have seen in detail how a field system will be, and again how the different types of field systems are there. So here we know that we can either use a permanent magnet or an electromagnet. We use electromagnet because it is easy to control the amount of flux that is given by an electromagnet, and if we want to increase the amount of flux that is required in the system, we can increase the amount of flux required, amount of flux that is being given to the system. So in order to maintain how much of flux is being given to the system, we generally go for an electromagnet rather than a permanent magnet. So permanent magnet will have, as the name itself indicates, the amount of magnetization given by a permanent magnet is constant, whereas the amount of magnetization given by an electromagnet differs depends upon the amount of current which we are giving to the electromagnet. So because of this advantage, we are going for electromagnets. In those electromagnets, how they are being how these electromagnets work means, we'll be having a ferromagnetic material where a wire is being wound on the ferromagnetic material such that whenever current passes through that wire, the total material will act as a magnet. That is the electromagnets. Okay, and we have seen how these are being connected, and how many how many coils will be there, where they are being mounted. All these things we have seen. Right, this is the field system. Again, we have seen that in this field system, poles will be present on which these field coils are being mounted. These poles again will be um, laminated, and all those things we have seen. All right, in the same manner we have seen what is an armature core. Armature core is nothing but a cylindrical arrangement where the armature windings are being placed. So how the structure of the armature core is there, all those things we have seen. Again we have seen what is an armature winding, and how we are why we are calling this as an armature winding. All those things we have seen. Again we have seen a commutator. We have already completed the commutator in the previous classes, and again in the last class also we have seen what is a commutator, and how this commutator is being designed, and what is the purpose of the commutator, and all those things. And then the last point which we have discussed in the last class was brushes, right? Why we are using brushes, what is the purpose of the brushes? The purpose of the brushes is just to collect the electricity, that collect the current that is being produced in the armature circuit and give it to the external load. That is the only thing the brush does. Okay, so we have seen different types of brushes and how they can be adjusted and everything. This is the total structure of the DC machine. Now we are going to see some of the features of the DC armature windings. Why we are going for this armature windings in specific means, in the last class when we were discussing about the armature winding and armature uh, armature core and all those things, we have said that armature windings have different type of structures, and depending upon our requirement and everything, we'll be choosing these armature windings. So we are going to see how these armature windings are affecting the amount of current or amount of voltage that is being produced in specific. Now, okay, so basically we'll start with the general feature of the DC armature windings, and then we'll go to some basic definitions, and then we'll understand what are the different ways in which these armature windings can be connected. So let's start with the general features of the DC armature windings. So as the name itself indicates, this is DC armature windings. This can be either used in a generator or it can be used in a motor. So either way we can use this machine. In general, we are talking about a DC machine here. So a DC machine, either generator or motor, generally employs windings distributed in slots over the circumference of the armature core. This we know, right? On the armature core, there will be slots in which there will be armature windings placed. Each conductor lies at right angles to the magnetic flux and to the direction of its movement. Therefore, the induced EMF in the conductor is given by, basically we know that how the induced, what is the equation of induced EMF in a normal, what do you say, in a normal circumstance, that is E is equals to BLV sin theta. He is saying that these conductors are being placed at 90 degrees with the magnetic flux as well as the direction of the movement. So sin theta, that theta is 90 degrees here, so sin theta is equals to 1. So here the induced EMF of the EMF in the conductor is given by directly E is equals to BLV volts, where B is the magnetic flux density, that is how much amount of flux is being passing through a single area, that is the magnetic flux density, which is measured in Weber per meter square, and then L is the length of the conductor in meters, and V is the velocity of the conductor. B is equals to BLV volts is the amount of voltage that is being induced in the conductor, okay. This is the first thing which we need to understand in case of a DC armature windings. So the armature, that is the first thing. The second thing is the armature conductors are connected to form coils. We know that two conductors are connected in a loop to form one whole coil, right? So here you can see in this diagram, you can see how they are being connected. If you remember, we have taken, actually in the simple loop generator, we have taken two of the names, right? That is, okay, AB and CD, right? So these are nothing but these coil sites AB, C, sorry, D. So these are the coil sites A, B, C, D. So how we are connecting this means, in the front, that is AC, this is AC, this is called as front of the coil. These two will be connected to the commutator. These two will be connected to the commutator. Okay, these two will be connected to the commutator. The back ends of these two, these are called as the back ends. These are called as the front ends. So front ends will be connected to the commutator, whereas the back ends are connected to each other, which is why this connection between the back ends is called as the back connection. Here, what we are going to make sure here, what is the main thing which we need to make sure means, here we need to make sure that one of the conductor is under one of the poles. That is, if you see here, this conductor AB is under the influence of the north pole. We need to always make sure that the conductor, one side of the conductor is under one pole, the other side of the conductor is on another pole. Okay, the other side of the conductor is placed under the influence of another pole. This is the main criteria for us to understand how these are being placed. Okay, so we need to always make sure that one of the coil sides, this total thing is called as a coil, so this one is called as a coil side or a conductor. So that one coil side or one conductor is under one influence, that is one of the poles influence, and again the other side of the coil should be in the opposite pole's influence. That is this span which we need to maintain for this to happen, that is for AB to be under north pole and CD to be under south pole. the distance between these two is called as the pole pitch. The distance between these two is called as the pole pitch. Okay, this is an important definition. We'll see this in particular, but you just understand here. Why are we doing this? Why are we making sure that one of the coil side or one of the conductor is under one pole and the other conductor is under another pole? Means in this way, if we maintain in this way, then the EMF induced in AB will aid the EMF induced in CD. The EMF induced in AB will aid the EMF induced in CD, and this will form a closed circuit, and this will form a closed circuit. This also we have seen in case of the simple loop generator. There we have seen that the direction of current or the direction of the induced EMF in AB and CD will be aiding each other such that the current will be flowing in one direction only in both of the coils. So that's why we need to make sure that one of the conductor is in the influence of one of the pole, and the other conductor side, the other conductor or the coil side is under the influence of the opposite pole. Okay, so this is the basic armature, this is the basic structure of the armature coil. Okay, here he is giving us the description. Basically we have the basic components of all types of armature windings is called as the armature coil. Figure that 1.131 shows a single turn coil, that is it has two conductors or coil sides connected at the back of the armature, as we have seen here. Now figure 1.132 shows a 4-turn coil which has 8 conductors or coil sides. So this is just 1-turn coil, that is this has only one turn. Now if you go for this 1.13 second figure, that is the figure which we are seeing here, in this case we have four conductors connected back to back with another four conductors. Four conductors are connected back to back with another four conductors. This type of arrangement is called as a 4-turn coil. This is called as a single turn coil because only one pair of conductors are there. That is only one conductor under the influence of a what do you say, this one, under the influence of one pole. Here in this case, if we just understand this, here there will be one pole and here there will be another pole. That means we have four conductors under the influence of north pole and corresponding four conductors in under the influence of the south pole. This type of coil is called as a 4-turn coil. This is just an example, ma. Like this, it can have any number of turns. That is not only 4 turns, it can have 5 turns, 6 turns, 7 turns, any number of turns it can have. The only thing is you need to understand how many number of conductors are present in this 4-turn coil. That is 4-turn coil has 4 into 2, 8 conductors. That is 4 conductors under north pole and 4 conductors under south pole. This is what we need to remember. Okay. So there are two types of coils, basically single turn coils and multi-turn coils. In this case, it is showing 4-turn coils. The coil sides of a coil are placed a pole span apart. That is, one side of the coil is under north pole and the other side is under the next south pole at the corresponding positions as shown in the figure 1.131. That is what we have seen. So this span is called as the pole span. Okay, so pole span is nothing but nothing but making sure that one of the conductor is under one pole while the next conductor or the next coil side is under the opposite pole. Okay, Consequently, the EMFs of the coil sides add together. That's what we have seen, right? If the EMF induced in one conductor is 2.5 volts, then the EMF of the single turn coil will be 2 into 2.5, that is 5 volts. Each conductor is having 2.5 volts. So two conductors are there, 2 into 2.5, 5 volts is there. For the same flux and speed, the EMF of a 4-turn coil will be 8 into 2.5, that is 20 volts. Just understand this. Now, for one coil, you have 2.5 volts. Here we are having, one coil side, you have 2.5 volts. Here we are having 4 coil sides, 4 plus 4, 8 coil sets, that is 8 into 2.5, 20 volts. So just by looking at this number, you can understand why we are going for multi-turn coils. Here, by using just a single turn coil, we are just getting small amount of voltage, whereas if we go for a multi-turn coil, we are getting more amount of voltage for the same flux as well as the speed of the machine. We are not changing the flux density of the machine, and we are not changing the speed of the machine. By just maintaining the same flux as well as the same speed of the machine, by using a multi-turn coil, you are getting much more EMF than a single turn coil. That's why we will be going for multi-turn coils in an armature. Okay. Next point which we need to understand, that is the third point which we need to understand, is most of the DC armature windings are double layer windings. That is, there are two coil sides per slot. We'll see, okay, two coil sides per slot. Here, we know this is a slot, right? This is a slot of armature. This is a slot on armature. Generally, what we'll be doing is there we can put only one coil side in that slot, or we can put multiple coil sides in the slot. Okay, so basically what we'll be doing is we'll be going for a two layer winding. Basically, what we are going to do is in one slot we are going to put two coil sides will be placed in one slot. That is why it is called as a double layer or two layer winding. Let us see. Okay, one coil side of a coil lies at the top of a slot, and the other coil side lies at the bottom of some other slot. So you need to understand that if you are taking a conductor, total conductor, if you're taking a total coil, then one coil side, if it is on the top of a slot, then the corresponding coil, that is, if AB is in the top of the slot, then CD will be at the bottom of the some other slot. Okay, if AB is at the top of one slot, then CD will be bottom side of the another slot. That is how the arrangement are there. The coil ends will then lie side by side. So what happens, why we are doing this means, sorry, why we are doing this means, here I'll just show you how the connection will be. So here, if we are saying that top and bottom, that means this 1 and 4 will be one pair, 1 and 4 will be one pair, and similarly 3 and 6 will be one pair. So how it will be means, one, if one is here, and again two slots are there like this, if you understand that two slots are there, then 1 and 4 will be connected something like this. Okay, sorry, okay, I'm not able to draw it, but actually, so like this, if you see, 1 and 4 will be connected, and then this 2 will be connected to some other thing, right? So that connection will not overlap with this previous connection. That connection will not overlap with this previous connection. That is why we are going for this type of arrangement. That is, 1 and 4 will be a pair, as well as 3 and 6 will be a pair, some 5 and something will be a pair, and 2 will be paired with some other slot, like that, some other coil side. Okay, the two coil ends will then lie side by side. That's what we were saying. The in two layer winding, it is desirable to number the coil sides rather than the slots. If you are having only a single layer winding, then we can just, if you know which slot, we can number the slot such that we know only one winding is there in that slot, and we can understand where the connections are there. But for a two layer winding, we need to make sure that the slots are, whether the slots are numbered or not is a secondary question, but the coil sides have to be numbered such that we can locate where the other pair is, the coil sides are numbered as indicated in the figure 1.14. That's what here he is saying, how the sides are numbered. The coil sides at the top of the slots are given odd numbers, and those at the bottom are given even numbers. So we need to understand, this is a very important rule. We need to understand that the top coil sides on the top side are given as the odd numbers, whereas the coil sides at the bottom are given even numbers. So we need to definitely remember this: top odd numbers, sorry, bottom even numbers. Okay, this is very important, just remember that. Okay, the coil sides are numbered in order around the armature. So how are they being numbered means they will be numbered in the same order throughout the armature. The coil sides are nearly a pole pitch apart. So we need to make sure that the coil sides are nearly a pole pitch apart. That is, the first side of the coil should be under one pole influence, the other side of the coil should be under another pole influence. In connecting the coils, it is ensured that the top coil side is joined to the bottom coil side and vice versa. So that is how we are going for the connections. The coil side 1 at the top of a slot is joined to coil side 10 at the bottom of another slot about a pole pitch apart. He is just giving us a definition. Okay, coil side 1, here you can see coil side 1 is connected to 10. Here I'll just try to show you guys. Here 1 is there, that is being connected to, just understand this, that is being connected to 10 here, that is being connected to 10 here. You can see the connection also. Here you can see the connection. Okay, so you need to understand how these are being connected. Okay, one is being connected to 10. Okay, in the similar way, coil side 12 at the bottom of the slot is joined to a coil side 3 at the top of another slot. Here also you can see that, also you can see 12 and 3. This is 12, this is 3. Here you can see those two are being connected. 3 is being connected to 12. 3 is at the top of the slot. Here if you see this, in this slot 3 and 4 are there, but 3 is at the top, and here 11 and 12 are there. 12 is at the bottom. We are making sure that the top of one coil and the top coil of one slot is being connected to the bottom coil of another slot. Okay, it may be noted that as far as connecting the coils is concerned, the number of turns per coil is immaterial. So here if you are just understanding this, number of turns of per coil is a different matter, that is a different situation, but here the connections are, how they are being numbered is important. For simplicity, then the coils in winding diagrams will be represented as having only one turn, that is two conductors. For our understanding and for the simplicity, we'll be going for winding diagrams, that is how these windings are being placed and how they are being connected. in the future classes we will be seeing how these winding diagrams will be there. So in those winding diagrams, for simplicity purpose, we are not going for multi-turn coils, we are going for only single turn coils. That is, we will understand only, we will assume that our coil has only single turn, that is only two conductors are being connected for each coil. Okay, so this is the connection diagram. Just understand how this is being connected. Is as I've mentioned in the previous in the starting of the, I mean in the previous topic, the this is called as the back of the armature, this is called as the back end, and this is called as the front of the armature, that is the front end. Okay, I'll just try to write it. Back end, front end. Okay, back end, front end. Cool. So the next point, that is the fourth point which we are going to see, is the coil sides are connected through the armature segments in such a manner as to form a series parallel system. A number of conductors are connected in series so as to increase the voltage, and two or more such series connected parts in parallel to share the current. So this we know, right? We have already seen that a series and parallel connection will be present between the conductor systems, such that such that the parallel system will give us the high amount of current, as well as the series system will give us the high amount of voltage. This we have already seen. All right, so sorry, so the he's just telling us that this is being connected, that is the series and parallel connections will be done. Figure 1.16 shows how two coils connected through commutator segments A R C have their EMFs added together. Here let us see, in this figure 1.16 is saying that the EMFs are being added together. Okay, now if the voltage induced in each conductor is 2.5 volts, this is not 2 to 5 volts, 2.5 volts, then the voltage between the segments A and C is 4 into 2.5, that is because we are having two conductors per side of the upper pole here. So 2 into 2, 4 will be there. 4 into 2.5, 10 volts will be generated between the segments A and C. It may be noted here that that in the conventional way of representing a developed armature winding, full lines represent the top coil sides, that is coil sides lying at the top of the slot, and the dotted lines represent the bottom coil sides, that is coil sides lying at the bottom of a slot. So just understand this. Top coils are represented with solid lines, whereas these dotted lines are nothing but the coils which are under the, that is the uh, bottom of the slot. Top of the slot, bottom of the slot. Top of the slot as well as the bottom of the slot. Okay, that is the general convention which we will be following. Okay, the last point which we are going to see under this general characteristics of the DC armature windings is the armature windings is a closed circuit winding. Closed circuit winding, that means there is no another path other than that winding. There is no another path for the current to pass through other than the winding. In such a winding, if one starts at some point in the winding and traces through the winding, one will come back to the starting point without passing any external connection. That is how we are going to make sure that our armature winding is a closed circuit winding. So we will not have any other path. We will make sure that if you start at one point and trace the connections and everything, you will come to that another point from the, you will come to the starting point without passing through any external connection. Okay, DC armature windings must be of closed type in order to provide for the commutation of the coils. So for the commutation to be for commutation purpose, we need to make sure that our armature winding is a closed circuit winding. Closed circuit winding. Okay. So these are the general things which we need to understand for the DC armature windings. Okay. So basically what we have seen is, we have seen what is the amount of voltage that is being generated in this particular the armature winding, and we have seen different types of armature windings, that is the single turn coils as well as the multiple turn coils. And then we have seen what is the voltage if we are using, what is the advantage for going for a multi-turn coil, that we have seen. And again we have seen double layer windings as well as the single layer windings. Why are we going for the two layer windings, why are we going for the single layer windings, that we have seen how they are being connected and all those things. And again we have seen uh, how these are being connected in series as well as parallel systems, why we are going for the series, why we are going for the parallel, all those things, and what is the conventional way of representing the developed armature windings. So if you can see here in this diagram, you can see that the solid lines are nothing but the coil sides which are at the top of this slot, whereas the dotted lines are the coil sides which are at the bottom of the slot. This is a convention which we will be following throughout our subject. Okay. And again we need to ensure that our armature winding is a closed circuit winding. That is, the if we start tracing one winding, we should come back to the starting point without passing any external connection, such that because of this type of connection, only this type of connection will provide us the ease to go for the commutation of the coils. Okay. For this sorry, for the commutator to work, this type of connection is compulsory. So these are the general characteristics which we need to follow for a DC armature winding. So next we will see a small definition which is called as a commutator pitch, which is represented by YC. The commutator pitch is the number of commutator segments spanned by each coil of the winding. It is denoted by YC. So for for one total coil, each conductor, how many commutator segments are being used. That is, if one coil side is here and then the other coil side is in some other way, how many commutator segments are there between these two coil sides is what is called as the commutator pitch. Let us see in figure 1.17. One coil side of the coil is connected to commutator segment 1, the other side is connected to commutator segment 2. Here you can see commutator segment 1 is being connected to one side, and the commutator segment 2 is being connected on another side. So here, therefore, the number of commutator segments spanned by the coil is 1. Only one coil, one commutator segment is used, is between those two coil segments. So YC will be equal to 1. Whereas, if one coil side is connected to commutator segment 1 and the other coil side is connected to the commutator segment 8, then the number of commutator segments spanned will be 8 minus 1, that is 7 segments. That then the commutator pitch will be YC is equals to 7. That is also shown here. Here you can see it. Here first coil side is connected to 1, but the second coil side is connected to 8. So 1, 2, 3, 4, 5, 6, 6 and 7. So 7, 8 minus 1. 8 minus 1 will be your commutator pitch. Okay, here 2 minus 1, that is 1 will be your commutator pitch. Here 8 minus 1 will be your commutator pitch. The commutator pitch of a winding is always a whole number. Okay, you should remember this. Commutator pitch will always be a whole number. Since each coil has two ends, and as two coil connections are joined at each commutator segment, therefore the number of coils is equals to the number of commutator segments. So each coil has two ends, and two coil connections are connected at a commutator segment. Okay, so two coils are being connected at a commutator segment. Two coil sides are being connected to a commutator segment. That is, one coil is being connected to one commutator segment. Similarly, So we can just understand that one coil is equals to one commutator segment. So number of coils, how many number of coils which we are using is equals to the number of commutator segments that we need in that commutator. For example, if an armature has 30 conductors, the number of coils will be 30 by 2, that is 15 coils will be there. So therefore the number of commutator segments is also 15. So we need, if 30 conductors are there means the conductor is nothing but one side of the one coil side, right? So how many coils will be there? 30 by 2, that is 15 coils will be there. 15 coils are there means we need 15 commutator segments. Okay, note that commutator pitch is the most important factor in determining the type of the DC armature winding. So we need to understand that this is a very important concept, that is a commutator pitch is a very important concept because it will determine the type of DC armature winding. We will see different types of DC armature windings. So by just looking at this commutator pitch itself, you can say whether what type of armature winding we are using in this particular machine. So it is a very important concept. So just remember that this is a very important concept. Okay, so this is the commutator pitch. So the last definition which we'll be seeing for this today's class is pole pitch. It is the distance measured in terms of number of armature slots per pole. So pole pitch is how many armature slots come under one influence, one pole influence. That is what pole pitch is. How many armature slots come under one pole influence. Okay. Thus, if a 4-pole generator has 16 coils, then the number of slots is equals to 16. Therefore, pole pitch is 16 by 4, that is 4 slots. So, 4 slots per pole. So, number of coils first we need to understand, then number of slots we need to understand. If you know number of slots, then you just need to divide the number of slots by number of poles. Also, pole pitch is equals to number of conductors by number of poles. 16 into 2, that is 16 into 2, that is 32 divided by 4, that is 8 conductors. We can either talk about how many slots per pole, we can talk about how many slots per pole, or we can talk about how many conductors per pole. Depending upon our requirement there, we can either tell that pole pitch, we can either represent the pole pitch in number of slots, or we can represent the pole pitch in number of conductors. So if we talk about slots, then directly we can just divide the number of slots by number of poles. Okay, how many slots are there? Total number of slots by total number of poles. Then you will get the pole pitch in slots. If you are going for number of conductors, then total number of conductors divided by total number of poles. Then you will get in terms of conductors. Pole pitch can be represented either in slots or in conductors, depending upon our requirement. Okay, so let's stop the class here.